Hello, I am Masoud Dehyadegari from KN2C University of Technology, and I'm presenting our work on G-arrays, geometric arrays for efficient point cloud processing, done in collaboration with my colleagues Hoda Rudaki Lavasani from KN2C University of Technology and Mahdi Naz Bojuni from University of Utah. Point cloud processing is a rising field in computer graphics. A point cloud is a collection of individual points where each point includes 3D coordinates along with several attributes such as color and reflection. As we show here, point clouds are most commonly generated by 3D laser scanners and LiDAR technology. Today, we can see many devices around us that generate point clouds such as MRI machines, home robots, and mobile devices. The output of these devices must be represented in an efficient format being processed by various applications such as virtual and augmented realities, medical imaging, indoor navigation, and real-time 3D telepresence. Today's point clouds are represented in structured or unstructured formats. One difficulty in representing point clouds is the fact that a point cloud doesn't necessarily include all possible points in the 3D space. Therefore, representing geometry of points in the existing format is a significant challenge. An unstructured point cloud format is simply an unordered array of existing points in the point cloud as we show on the left. In contrast, we can use graph or tree-based data structures that employ links among nodes and points to some extent represent a relationship among points. One such data structure is KD tree or octree. As we show on the right, for an octree, the 3D space is divided into 8 octants. Each octant can be further divided to smaller octants if it has more than one point. The block division for forming an octree is repeated based on a user-defined parameter, namely depth. Unfortunately, the existing formats are not sufficient for high-performance point cloud processing. For the unstructured formats, we can take advantage of an efficient memory footprint and high spatial locality while processing points. However, such formats suffers from expensive linear scan while processing points. Moreover, such formats cannot hold any geometric relationship among the represented points. In contrast, the structured formats can hold a limited relationship among points, which enables accessing only a subset of points while processing a point cloud. On the downside, such linked formats require a larger memory footprint for data representation and suffers from memory indirection while accessing points. Instead, we propose a compressed searchable data structure that relies on array representation of the geometry of points. This format limits the number memory indirections to 2, take advantage of the spatial locality in array structures, requires a smaller footprint due to sharing coordinate across points, and keeps the geometry of points along each coordinate axis. On the right, we see 5 points in a 3D space. An example representation of these points using geometric arrays is shown in the middle of this slide. A RGB array stores the attribute values of the existing points in the point cloud. The remaining vectors can be classified into index or pointer vectors. The index vectors show the coordinate of the corresponding points in x, y, and z dimensions. The pointer vector stores the cumulative number of existing points with the corresponding coordinate. For example, a point with coordinate 10, 23, and 16 is shown in the right figure. In the middle figure, we can observe the value of different vectors. Also, a point with coordinate 30, 23, and 16 is shown on the right figure, and the corresponding values in the array are represented in the middle figure. To access a specific point in G-arrays, we should first determine if this point exists or not. In this example, here we are going to look up a point 20, 33, and 36. For this purpose, it is enough to refer to index 1 of x pointer array. If the difference between x pointer 2 and x pointer 1 is non-zero, there exists at least one point with x coordinate equal to 20. Then the pointers of x pointer 1 and x pointer 2 show the candidate locations for finding the corresponding y coordinate in the y-index array. Searching the cells with indices between these 2 points in the y-index array, the point with x and y coordinates equal to 20 and 33 could be found. Then the index of the point found in y-pointer array is used to find the corresponding z coordinate. The difference between y-pointer 3 and y-pointer 2 show the number of points with x and y coordinates equal to 20 and 33 respectively, and the pointers of y-pointer 2 and y-pointer 3 in y-pointer array show the candidate locations for finding the corresponding z coordinate in the z-index array. We examine our proposed format for temporal encoding in geometric point cloud compression. We need to remove spatio-temporal redundancy to achieve higher compression ratio. The geometry of points in point clouds, unlike the computer-generated or natural 2D videos, has limited spatio-temporal locality. The figure on the right showed 2 consecutive frames captured at different time instances for the 3D model of a soldier. Our proposed point cloud spatio-temporal encoding is based on G-arrays. In this approach, we consider the first frame of any input sequence as the reference for the second frame. We employ a special coding for the first frame based on the prior work on MPEG G-PCC as is shown in the right gray area. Then we consider the second pass for all the other frames as predicted frames, left gray area, which includes several steps for clustering points, estimating cluster motion, and generating point residual. The first step in the proposed temporal prediction technique is clustering, that is based on k-means algorithm. Motion estimation is used to describe the movement of textures or objects in the consecutive frames. In the motion estimation process, for each point of the predicted frame, we want to look for the most similar point in the reference frame. Hence, the corresponding cluster of each point in the reference frame is enough to find the most similar point. When the best matching block for a predicted block is found in the reference frame, the corresponding movement between the reference and the predicted block is represented by motion vector. In the proposed approach, we employ a coarse-grained motion vector estimation algorithm. This algorithm uses the centroids of the computed clusters in the previous step to estimate the motion vectors. After computing motion vectors, a reconstructed frame using the predicted frame and the estimated motion vectors is generated. The points of each cluster are displaced according to its corresponding motion vector. Finally, we should compute residual frame. The residual frame contains the information to correct the error of motion estimation process. We evaluate the performance of the proposed compression scheme using G-arrays and point clustering. We use 4 different sequences that capture human bodies in motion, such as soldier, long dress, loot, and red and black. We study the benefits of temporal prediction in the compression of geometry in 3D point cloud sequences. In our proposed approach, the frames of the sequences are coded sequentially. Each frame is coded in a way that its previous frame is considered as a reference frame. For the baseline method, all of the frames are coded using their best set of the parameters in the MPEG G-PCC open source library. The PSNR versus compression ratio curves are shown in these figures to compare the performance of our method with that of the baseline. The results show that the proposed method improves the compression ratio for various output qualities over the baseline MPEG G-PCC. To further evaluate the performance of the proposed temporal encoding, we consider a representative metric based on both quality and the compression ratio. The goal is to simultaneously increase compression ratio and quality. The new metric is defined as the product of the compression ratio and PSNR, called PCR. We study various quantization parameters for our simulation, where the quantization parameter determines the number of bits representing each component of the points. Figures show the comparison of the baseline and our proposed method based on this metric. The results indicate that the proposed method improves the compression ratio and quality by averages of 13 to 30% over the MPEG G-PCC. We also evaluate the performance of the G-arrays as compared to octrees in terms of memory consumption and point lookup speed. The table shows the memory requirement for our method compared to the baseline. Our method uses the G-arrays to store the points and search for the best matching ones, but the baseline method uses the octree structure. We observe more than 1.4 times memory saving for the G-arrays over the octrees. Moreover, the proposed G-arrays enable 16 to 54 times better point lookup speed as compared to the state-of-the-art octrees. Now let me just conclude the talk with highlights of the proposed architecture. G-arrays hold the promise for future efficient point cloud processing. The proposed format provides faster point lookup operation and less memory consumption compared to the state-of-the-art octree used by the MPEG G-PCC. A cluster-based temporal prediction approach was examined using the proposed G-arrays. The proposed temporal prediction approach improves the compression ratio and quality of the geometric point clouds. Thank you.